Okay, so we've learned about graphs, and we've written a type comment which looks exactly like the type comment for an arbitrary arity tree. And we've learned a new construct, shared, that lets us construct cyclical structure. Now let's do a template for operating on these house graphs, or these graphs of rooms. And let's think for a second about what we've got by kind of looking at this most complicated picture here. We've got, in some sense, a structural recursion because we know that our type comments are the same type comments as for an arbitrary arity tree. So there's sort of the structural recursion template we know we want to have. That's the one that comes from the template rules. But as we do with an arbitrary arity tree, it's probably good to encapsulate the two functions with local. Now these house structures are fairly small. There's at most 6 rooms here, but potentially it's very large, and certainly for a graph in general, it could be quite large. So let's make it tail recursive. And since it's an arbitrary arity tree-like structure, making it tail recursive is going to require a work list. Notice what I'm doing here. Because I have these clear notion of different contributions to the template, I'm kind of designing up the template structure that I'm going to want at this high level, at this almost model-like level. I'm saying, gee, I want all of these things before I've written a single open parenthesis. And what else might we want here? Well, remember, these house structures, even though they have the same type comments as an arbitrary arity tree, can have cycles in them. So that if you start, for example, let's look at the simpler one. If you start at A and you go to B and you go to C, you get back to A. And so if you're not careful, you're going to go around and around in circles. You're just going to keep going around and around. How might you solve that problem? Well, if you had a context-preserving accumulator, an accumulator that kept track of every room you'd already been to, then you'd be able to tell you were going in a circle. So if the progression of that accumulator values, for example, you start at the beginning at A, and that's an empty list, but by the time you get to B, that context-preserving accumulator is the list A. And what I'm going to do here this time is, even though I mean this accumulator value to be by the time we get to B, I'm going to put it on the link or the edge or the arrow, because in a graph, there can be more than one arrow that comes into a given room. And so the accumulator value might be different when we come along this arrow than when we come along this arrow. And you'll see that in just a minute. And by the time you get to C, it's the list AB. And by the time you get back to B, it's the list ABC. And you can say, oh, wait a minute, we've been here before. Let's stop. Let's stop right now because B is in the list ABC. So it'd be nice to have a context-preserving accumulator where have we been? And I'm running a little bit out of room here, so I'll just put a line break right here. What rooms have we already visited? So now I've actually done the hard part of designing this template. Now the reason I'm putting all this stuff together in one template is because when I think about it, when I think about any function that's going to operate on one of these house graphs, I'm going to want all of this stuff. So I might as well put it in the template to start with. So let's go ahead and code this template. Let's see. It's structural recursion encapsulated with a local. So fun for, I'll call the outer function house. And it's going to take some outer room R0. And then there'll be 2 inner functions. Fun for room R, and fun for list of room R. And there'll be a trampoline like that. So I've got the outer functions encapsulated with local. Now let me follow the structural recursion template rules to template these 2 functions. Let's see. It's compound data, so it's ... room name of room. That's a string, so we're done. Room exits of R is a list of rooms, so we'll call the other helper function using the reference rule, and that gets us that. Now let's do this. This is a classic list of template. If the list is empty, ... otherwise, ... first of LOR, but that's a room. So the reference rule does fun for R. Now I don't mean fun for R, I mean fun for room, first of LOR. And then this is the self-reference for the natural recursion, fun for LOR, rest of LOR. Okay, so at this point, I've crossed off the first two things in my template design. Let me just run it to see if it's well formed. It is well formed, at least. So we've done the first two things. Now let's add a work list to it. Now we know that when we add a work list to a arbitrary arity tree traversal, and these are the type comments for an arbitrary arity tree, we end up renaming this parameter. We don't have to rename it, but it looks a little prettier if we rename it from LOR to to-do. And let me do that everywhere, there, there, and there. And now we're going to add this to-do, the work list, to this other function. We'll put it after R. It could go before, but we'll put it after. And that means there's going to need to be something there. And this doesn't get anything else because it's already got the one parameter. Something's going to go here, of course. But remember, the reason we're doing a work list is to make it tail recursive. So this stuff has to go. I'll just cut it for a second. And instead of passing just the exits, what we really need to do is append the exits onto the front of the existing work list. And now kind of we're not doing anything at all with room name. So I'm just going to put a note, little, just in parentheses here, that you might, in an actual use of this template, do something with room name. It's just a reminder to me that it might be useful. Now let's see, in the case of the empty to-do, what are we going to do? Well, we still don't know. But again, this, we have to get this to be tail recursive. So in the work list accumulator, what happens is it becomes fun for room first to do, and then rest to do, like that. And then the work list starts out as empty. So let's see. We've got this work list parameter here to do. Let's say that it's an accumulator. To do is list of room, a work list accumulator. And we made this nicely tail recursive. We just call fun for LOR by adding the exits of the current room on the to-do list. And this template right now isn't doing anything with the room itself. So that's why we put this here, is you might want to actually do something with the room itself in a specific function that uses the template. Fun for LOR, if the work list is empty, does something. Otherwise, it just calls fun for room with the first thing on the to-do list and the rest of the to-do list. So now we've got tail recursive with a work list. But this thing will go around and around in circles. This thing will definitely go around and around in circles because it never asks itself the question, have we already been here? So now we'll add another accumulator. Let's see, we'll call it visited. And there's a couple different ways for this accumulator to work. One is for it to be a list of room, one is for it to be a list of room name. Let's just do it as a list of room name. context preserving accumulator, comma, names of rooms already visited. So let's see, we'll add it here, visited, and we'll add it here, have to add it to both functions. Something's going to go here. And now what happens in fun for room? Well, now we need to be careful to not do anything with the same room twice. So what we're going to do is, and here we're going to start to use this, so I'm going to pick this up. And what we're going to do is we're going to say, well, if this room name, the name of the room we're coming to, is a room we've already come to. In other words, if this room name is in visited, there's a special function member that does that. If the name of this current room is already in the visited list, then what do we got to do? Well, we're going to call fun for LOR, and we're just going to kind of, in some sense, skip this room. We're not going to do anything. So we call fun for LOR directly with to do, and the current value of the visited accumulator. But if we haven't already been to this room, then we'll call fun for LOR with more on the work list, and we also need to say, and this room's name is on the visited list. So this call to fun for LOR says, go ahead and add this room's exits to the work list, and add this room's name to the visited list. And I'm still going to leave this little comment here because specific functions that use this template might want to do a little bit more with the room name. You saw how it was convenient here. Now let's see, what does fun for LOR do? Well, when the to-do list is empty, it's still got to do something we don't know what yet. Remember, this is still a template, even though it's starting to be a pretty rich template. But now when it calls back to fun for room, it takes the first thing off the to-do list. That's the first. It passes the rest of the to-do list, and it also has to pass a new value for visited. But going through the list of rooms doesn't change visited. Okay? It's fun for room that's going to change visited, so we'll just put the old value of visited there. And what's the initial value of the visited accumulator? Well, it's empty. So revisiting, the visited accumulator, it's a list of string. It's the names of the rooms already visited. It starts out as empty. Each time we get to a room, we make sure we haven't been there before. If we have been there before, we kind of skip it. If we haven't been there before, we add this room's exits to the to-do accumulator, and we add this room's name to the visited accumulator. And then in fun for LOR, we just kind of go through the to-do list. So that's our template. Let's check its well-formedness. Looks pretty good. It's not running, of course. Notice how at this point in the course, our ability to understand that templates come from multiple sources and that we can blend them together and that we can do that kind of design up at the design level. We can write a note that says the template is structural recursion encapsulated with local, tail recursive with a work list, and a context-preserving accumulator, which is what rooms we've already visited. We can sort of have that design thought, systematically turn it into code, and now we've got this very useful template. Now that we've got this template, we can start to write some functions that operate on these graphs.